Good afternoon. So I'm going to talk about work done in my group over the past few years that have to do with optimization, numerical optimization. And the key word is constraint reduction. Okay. So work was done with a number of people, as I said, including Upsil from Catholic University Louvain, Cory Haak at Oak Ridge National Lab, Diane O'Reilly from the Computer Science Department, and these are students of mine and of Diane O'Reilly who have participated in this research. And these are a few references. My slides will be available. In fact, these are just references to our work that I will talk about. Okay. So I will start with a refresher or maybe a primer for some on a few things about linear programming. And so this slide is quite full, but it's because so the refresher is a slide and a half essentially. So at the top, this is a linear program, or actually nowadays you say linear optimization. People in the optimization community do not say linear programming, they say linear optimization. So this is still a linear optimization problem, right? Linear because the cost function we want to minimize is linear in a variable x. You have linear inequality constraints, linear equality constraints, I'm sorry, and inequality constraint, also linear. In its canonical form, the inequality is just non-negativity of the variable. So all is linear. To this problem, you can associate another linear optimization problem, also linear objective function in the variable y, linear inequalities, or affine, if you will, in y. Which, by the way, this inequality can be equivalently written like this, where S is an additional variable, S non-negative, and A transpose Y plus S equal to C, that's equivalent to that. Why is this called primal and is dual? By the way, we have the same matrix A here and here, the same vector C here and here, same vector B here and here. Okay. Let's first define the optimal values. The optimal value of this optimization problem is, by definition, the infimum of the objective function subject to satisfying the constraints. So among all the points satisfying the constraints, by the way, this set can be thought of as a polyhedron. So of all the feasible point x, the least cost is called the primal optimal value, because this is the so-called primal problem. And then the dual optimal value, it's a maximization, so the soup of the objective function subject to the constraint being satisfied. Okay. A very important result about linear programming, which to some extent holds for convex optimization in general, but there's a little more in the context of linear programming. Suppose that either this one or this one is finite. By the way they could not be finite, there are two ways this may not be, the optimal value may not be finite. One way is when this linear function is unbounded from below on that set. Right? So it could be that you can achieve as low values, if you will, without violating the constraints. And you say that the inf is minus infinity. It could be infinity plus infinity, and that's by convention. If the feasible set is empty, then by convention the optimal value is plus infinity. Now, if either, and then similarly for this one, if either one, Vp or Vd is finite, then they are both finite and equal. So the only case they are not equal is that one is plus infinity, the other one minus infinity. So one is feasible, the other one is unbounded. That's the only way duality. This is called duality. It's not achieved. So that's one sense in which they are dual of each other. Now, another interesting thing is this. So this is a convex optimization problem, right? Because linear functions are convex. On convex constraint optimization problems, the optimal value, and by the way, I should have said one more thing. If one of them is finite, they both are finite, and both are attained. Attained means that there exists an x that achieves this infimum value. So infimum is a min, and same thing for y. Okay, so if you have a convex problem, a value x or x hat is a solution to achieve the inf if and only if two conditions, in fact 3 conditions. One condition is the Lagrangian associated to this problem is stationary, derivative is equal to 0 with respect to x. Second condition is that you need x to be feasible, satisfying the constraint. And third condition, you need so-called complementary slackness, which means that a so-called multiplier, so I will talk a little more about that in a minute, multiplier associated with a constraint can be non-zero only if the constraint is active. So let's look at P. So x hat solves P if and only if we have feasibility, which is the first, it should be an x hat by the way, feasibility, the two constraints are satisfied. Second, there exist so-called KKT multipliers, and I call them S and Y tilde for this problem, and for good reason. S and Y tilde are my multipliers, such that this is 0. This is in fact the gradient of Lagrangian, which is 0. And third, complementary slackness. That means that the multiplier, which is associated to the inequalities, and this multiplier associated with the equalities, multiplier can be positive, strictly positive, only if the x corresponding s component is 0, meaning the constraint is active. Okay. So you have these 3 conditions which are if and only if for optimality. Similarly for y, you also have 3 conditions, but interestingly, feasibility means that, so this is satisfied, meaning that this is greater than or equal to 0. Okay. Okay, and the Lagrangian equal to 0 is exactly this, minus b plus a x tilde is 0, and finally complementary slackness is this again. So if you look at this, you have in fact the same conditions, the same conditions for the primal and the dual, right, which is summarized here. So x solves p and y solves d if and only if there exists S such that these conditions are satisfied. Okay. So this was the gradient of Lagrangian for the primal and feasibility for the dual. This is feasibility for the primal and gradient of Lagrangian for the dual. And this, which is, by the way, capital X and capital S are diagonal matrices with the xi's and si's on diagonal. So the entries of this vector are just xi, si. And the same entries of this vector. So this says that xi, si is 0 for every I, which is complementary slackness. Yeah. And non-negativity of multipliers. So these 4 conditions are if and only if, both for the primal and for the dual. So if you can solve these 4 conditions, you have solved both the primal and the dual at the same time. Okay. Now, so this talk is about interior point, so-called interior point methods. In fact, primal dual interior point methods. Now, one way to think about those methods is starting from this and starting from current guesses, which are strictly positive x and s. The components are strictly positive. okay, for reasons that I will point out in a minute, and some y, so initial guesses. Take the Newton direction for solving the equalities in a perturbed version of 1. So there is 1. This is the perturbed version, perturbed in two ways. One way is, well, here I had xi equal to 0. Here I have xi equal to a positive number. Okay? And the second way is that this non-strict inequality becomes a strict inequality. Now, the reason I replace 0 with tau positive is because it can be, both from experience and from the theory, it turns out that you can solve the problem much faster if you don't aim right away for 0, but you first aim to have both, to have all of these products to have the same value. This is called the central path in interior point optimization. So all of the products xi, si have the same tau value. Okay. And then we are going to drive tau to 0. Okay. So this is a la homotopy or continuation. Okay. So first aim for positive tau. And in fact, the tau that you aim for is the current average of these values, as noted here. And tau, in fact, is sigma times mu. Mu is just the average of the xi, si, of the current xi, si. Okay. So you aim for the average value, not exactly, you aim for something slightly less, sigma between 0 and 1, okay. Because you are trying at the same time to drive tau to 0. Okay. Okay, and so Newton direction, so you take the three equalities here, and you write the Newton iteration. By the way, Newton is linearization so you solve the linearized problem. Now the first two are linear in x, y, and x, and s. Only the third one is nonlinear. So linearization only affects the third one. And when you linearize, you get this. And so you are going to solve for delta y, delta x, delta y, delta s, and this is going to be the Newton direction. The step to be taken in the Newton direction is then selected in such a way that strict inequalities are preserved. And why do we want strict inequalities? Is because in order for this system to be well defined, for this matrix to be non-singular, you need these two diagonal matrices to have non-zero positive diagonal entries. Okay? Another condition you need, which is if and only if, we have three conditions, the one I just said, and A should be full row rank. And that's if and only for the matrix to be non-singular. Okay? So that's Newton direction, and then you take a certain step in a direction. The step should mainly ensure that x and s remain positive. Apart from that, you should go essentially as far as you can. Okay? And by the way, this mu, which is the average values of the xi, is in fact n times nu. N is the dimension, the number of I values, is the duality gap when x and y are feasible. So this has to do with duality gap, which is the distance between the current cost for the primal problem and dual problem. We are trying to narrow them down because the solution, you know, Vp is equal to Vd. Yeah? But currently you have a gap, and if your points all satisfy the constraint primal and dual, then that gap is equal to x transpose s. Okay, so that's the primer on linear programming and interior point methods. Commonly, now this system that we have to solve. Sorry. Okay. This system has lots of big zeros, and you can take advantage of that. You can do a block Gaussian elimination. If you do that and eliminate both x, delta x, and delta s, you can eliminate both delta x, delta s, and you are left with delta y, and you get an equation like this, where m is given by this. So we have an m cross m. Yes? No? Okay. Now, the dominant cost So the dominant cost in one iteration, by the way, is computing these directions. The line search, the cost is much lower. Solving the system is the dominant cost. So you can solve it by first doing block Gaussian elimination formally, and you end up with this system, which is size only m cross m compared to the side before. It turns out that the cost of forming M, of computing this matrix product, is the dominant cost. The other cost is to solve this linear system. This matrix is symmetric. You can use Cholesky decomposition, and the cost is m cubed over 3. M being the dimension of capital M. Yeah. Whereas forming the matrix, which you can write like this, by the way, these two matrices are diagonal, so it's not that bad. S inverse and X are diagonal, so this is in fact this sum. Yeah. And you have n terms, and each term takes m square flops to compute, so n m square, compared to m cubed over 3 for doing the Cholesky factorization, and n being the number of constraints of the dual. Right. So m is number of constraints of the dual here. N is usually larger than number of variables. So this is dominant cost. And so in view of that, we were interested in problems which have many more inequality constraints. In the dual problem, in this problem here, so many more constraints than variables here, many more inequality constraints than variables. And there are lots of problems in the category, as I point out later. So in that case, if you could somehow use a small number of constraints, instead of n here, if you could use only half of the constraints and still do a good job, you will gain half of the CPU time. Possibly you can reduce it more than that. So this is the idea behind constraint reduction. So these pictures are both in a dual space. It's a Y space. So in a Y space, this is the problem. We have inequality constraints. So Y lies in R2, in the plane. Y is in R2. The inequality constraints, we have in this case 13 inequality constraints, and we have drawn the constraint boundary. So the feasible set is the gray region. Okay? So in this case, suppose that so the B vector has not been drawn there, but is pointed kind of in this direction in such a way that this maximizes B transpose Y, this point here. Okay? And whenever the problem is non-degenerate, in fact, the solution will be on exactly 2 constraints in R2 and exactly M constraints in Rm. Right? So suppose that the solution is here, and we have all of these constraints. The interior point method will solve a linear system involving all the constraints, and will come up with a certain direction delta x. In fact, in this case, if we knew that only these 2 constraints are active, then we can solve the problem in one shot just by solving the system of equations. Okay? Of course, we don't know which are active. That's the main difficulty in solving the constraint optimization problem, which constraints are active. But we might have an idea of what constraints are more likely to be active, okay, from whatever. So we'll talk later about how you could possibly try to pick that. But if we knew that some of these, some of them are completely irrelevant, and some of them are redundant because they don't affect the optimal solution. If you drop some of the constraints, like here we have dropped all the one time dashed lines here, and we kept only 6 constraints, which are in a set we call Q. So the optimal solution will still be the same. The direction will be different because the system we are solving will be different. It could well be better than that direction actually. But in any case, the cost of solving the linear system will be smaller. And so there was some work along such direction done in the early 90s. So our work focuses on primal dual interleaved methods, whereas the early work was for pure dual interleaved algorithms. Okay, so a little more details about what we are doing. So given a small set Q of constraints deemed critical, so Q is a set of indexes of constraints deemed critical for whatever reason at the current iteration. So compute a third direction for these problems, which are still dual of each other. This A sub Q, okay, let's first look at here. C sub Q is a vector C, but much shorter, because we have fewer constraints. Only those indices in Q are kept. And similarly for the left-hand side, only the entries in Q are kept. That means that only a few columns of A are kept, a few rows of A transpose, a few columns of A. The same AQ is used here. So here you have fewer variables, XQ, fewer variables in the primal than you had before. Yeah? So you have to solve, like before, we have this problem with all these Q's everywhere. And the normal equation now it becomes this, where MQ becomes this, same as before, except for the Q subscript. By the way, Q subscripts here also means that we have fewer entries in these diagonal matrices. And these two are diagonal matrices. We just kill all entries which is not indexed in Q. So the dominant cause is that of forming this so-called reduced normal matrix, which are with indexes Q, which is this. And the difference here is that the number of terms is now cardinality of Q compared to n before. We had nm square. These are the total number of constraints, and this number of constraints in the working set, so-called working set, the constraints you are keeping at the current iteration. So potentially you can save a lot per iteration if you pick a small set of constraints.
It's the same. It's the dimension that changes, right?
Yeah.
All the other properties are preserved.
Exactly. There's one that might not be, and I point out right here. So given some initial point, dual feasible, we need a dual feasible initial point. Key requirements for the working set Q should be sup K, not sub K, iteration K. Okay, there's one condition here. AQ must have full row rank. This is in order for this linear system to be well defined. So AQ must have full row rank. The A matrix of the original problem, usually people do pre-processing on the A matrix and it has full row rank. Now AQ depends on Q, which you will change at every iteration. So you cannot do pre-processing on there. So AQ may not be full row rank. So there's a difficulty there. Now the key property you need, the key condition you need to satisfy when you form your set QK is that if you have a sequence or a subsequence, the YK is the sequence constructed by the algorithms, sequence of dual variables. If a subsequence of it converges to Y prime, so Y prime is a limit point, then for K large enough, all constraints that are active at Y star must be contained in Q sub K. So as you approach a point, if you converge to a point, in order for things to go well, as you get closer to it, you need to include all the constraints that are active at that point. Of course, you don't know where you're converging to, right? So you cannot implement that as is, but you should come up with a rule which will have that property.